Hi students, in the last lecture we discussed about the impedance of a electrode interface wherein you had a solution resistance in series with the parallel RC circuit which is characteristic of the given electrode interface. Okay, so and we have actually derived the real and imaginary part of the impedance, and we have plotted them in the Nyquist format, and we have plotted them in a Bode format. Okay, so I hope you are familiar with that. Today I am going to introduce another element which is called Warburg impedance, that will be in series with the Faraday impedance. You know why? Because this Warburg condition is something related to the mass transfer. So as we discussed in the class, only if there is a mass transfer to the electrode, then there will be an electron transfer. So they are all sequential event. So therefore I have put them in series here. For example, let us consider the electrolysis of water, particularly the hydrogen evolution at the cathode. So I make the cathode as my working electrode, and I apply some potential on that with respect to my, say, reference electrode in 3 electrode system. So then this circuit, so here I have not shown the solution resistance, if we include that also. So that circuit will be the circuit that represent that cathode. Okay, so the proton is a species which has to diffuse towards the cathode in order to become hydrogen gas during electrolysis of water. So that means this Warburg impedance denotes the, the diffusion characteristic is a function of the diffusion characteristics of the proton in that medium. Okay, again this Barber conditions can be divided into two part, an RC circuit like this. So it has a capacitance part, it has a resistance part. So the solution, when the proton has to move in the solution, it will face some resistance. So that's what is shown here. So what is important to note here is this component here is a frequency dependent one. Why? Including this resistance here. So why? Because at very high frequency we don't alter this R. Okay, or it won't what I say, the R, I mean charge transfer reaction that is happening at some particular DC potential. If you impose a AC voltage waveform on it, the imposed AC voltage waveform do not alter the R at that condition, right? So that means you don't see influence of this applied voltage waveform at that frequency here on the R1. So therefore the species which is moving in the solution, diffusing in the solution, also won't see. And also at such high frequency the species won't even feel that it has to respond to that frequency change, at that high frequency change. But as you decrease the frequency, okay, as you decrease the frequency, especially when the electrode is suffering due to mass transfer issues, so when you apply at low frequency, what happens? For certain time your electrode potential goes up. That will be your base DC potential plus the amplitude. For the next moment it will go down. That means the base DC potential minus the amplitude, voltage amplitude, right? So during that time, the what will happen is there will be a slight increase and decrease in the R1 value. Okay, because we are going to little higher potential over potential, and then we are coming to a lower over potential, right? So that means there will be a disturbance in the flux of the species that is going towards the electrode. So at that time this species also would respond to this frequency change. Okay, so that's when you will see this Warburg impedance, especially when you conduct at high over potential this measurement. You would see this Warburg impedance. At low over potential, what happens is you don't have any mass transfer issues setting up in the system, so you wouldn't see irrespective of the frequency, but especially at high over potential you would see that. The circuit is called Randall circuit. So now the Z1 is this part. Okay, the Z1 has R1 plus ZW. That's the impedance that is coming from the Warburg part. So again, this ZW can be split into a real and imaginary part as before, and the total impedance will be like this. Okay, that is in terms of C, Z, omega, and so on. Okay, so if you have a solution resistance, then you add the solution resistance here, and that becomes part of this real part as well, right? So then we can split the real part like this and the imaginary part like this. this um, total impedance. Okay, so at lower frequencies, what happens? At low frequencies, you will have only R1 and Z dash W. So you have this and this. At low frequency, this will be blocking. So actually speaking, you will have the solution resistance plus this and this at low frequency, and at and the real and imaginary parts becomes something like that. Okay, this will be the real part. This will be the imaginary part. So if you want further details on this, you probably can consult this literature, recent literature. So this graph shows that Warburg impedance in terms of time constant, because this, remember that I split this Warburg impedance into two parts. One is the capacitance and the resistance, right, which are in parallel. So if you multiply R and C, then you get a time constant. So this is represented in terms of time constant. So increase in time constant means if I say I fixed my capacitance, this increase can happen only because of increase in the resistance to the flow of, different to the diffusion of the species that is in the solution, right? So in the case of electrolysis of water, if you look at the cathode, it is a resistance upward to the diffusion of proton in that medium. Okay, so scenario, that first curve that is here is a scenario at lower time constants. That means when the resistance is low for the movement of the species. So as the time constant goes up, that means as the resistance of the medium offered to the flow of say proton goes up, then this becomes a little stretched and stretched. Finally, it becomes a spike like this. This is at 45 degree. Okay, so this is a typical impedance response, including the Warburg component into your Randall's circuit. And this first semicircle here is correspond to this RC here. Okay. Okay, so if you do this experiment at very low or potential, then you may not see the second semicircle, because this component will be very insignificant compared to the R value, so you wouldn't see this. So you will see only one semicircle in the system. Okay, so we can use this RCT value that we get. RCT is a charge transfer resistance or Faraday resistance that we get from the diameter of the semicircle to understand what is the rate constant of the reaction. So the relation is like this: 1 over RCT is related to this like this, where theta is the surface coverage of a species on the electrode, and Z is the number of electron transferred. K naught is the rate constant of the reaction at equilibrium, and F is the Faraday constant, and C naught is the concentration of the species. And theta can be defined using the over potential like this. This means surface coverage dictated by this. Okay, so and then so we can do this experiment at a bunch of DC potentials. So at each DC potential you will get one RCT. So then you get this curve. This is 1 over RCT. So with increasing over potential, RCT will decrease, so 1 over RCT will increase. That's what you get. So for now you just forget about this part of the curve. We'll only concentrate on this. Okay, so if you want to know what is the K naught of this system, okay, then what you can do is you can use this equation, assume some K naught value, assume some values for your C naught and alpha, that is a transfer coefficient, and theta is defined by your over potential. Then you can model the system and then simulate and check whether it is matching with your experiment data. If it is not matching, you have option of tweaking the E naught, because E naught is not fixed. If we change the conditions, instead of a standard condition we go to some other condition, that equilibrium potential there will be slightly different from the standard condition. So you can use E naught value, suitable E naught value, and then you can see whether it fits or not. If you change, generally when you change the E naught value, this curve moves left or right. Okay, when you change the K naught value, the intensity of this curve will change. Even in a CV, for example, the E naught changes, your CV moves left or right, but when the K naught changes, the K naught increases, for example, the CV will become, the current due to the reaction will become, now it will increase. So you will have a taller peak in such scenario. Okay, so with this we conclude the my teaching on the impedance. So also the this is the last lecture in CY 6998 from my part. So hope you enjoyed this summer despite having a lot of disruptions. So if you have any question, you can get back to me by email. We can have another session scheduled to clarify your doubts. Thank you.